how to go about measuring that. It's real simple if we've got a single zone unit like we use in our arenas and our big open areas, whatever. It's real simple then, because we can just put a duct mounted sensor into the return plenum, and we can get a good indication of how many people are in the space. But what if we get in an office environment like we have on this floor up here with a bunch of individual offices? How can we really detect that? So in those instances, we end up either not using this technique, or we end up with a lot of these sensors. And what I would say is if you had a 40-zone system, you need 10 to 20 of these sensors in that to get a really good indication, to really protect your people and get it, make sure that you have the proper ventilation rates. Modulating, what we're talking about there is the exhaust and the supply air to the facility. And a very powerful technique is to use the VFDs that we showed there, the variable speed drives, to again get that savings while getting a handle on the ventilation. Finally, recovery of the exhaust energy. So when we're running these buildings, every air that comes in, or as we add air or ventilation air, we have to take air out at pretty much the same rate. So the idea is here is trying to recover some of that energy because we're pumping out that 70-degree air out of the space. So that we've spent a lot of money to get to 70 degrees. We want to try to recover some of that, and I'm going to show a little bit of that technology. Reheat is the most common means to prevent this overcooling effect, and it's not one of my favorite products. This here is an example of an electric resistive reheat means, and I'm not a big fan at all. There's a lot of other means, but the advantages of the electric reheat is it's a very low first cost, low maintenance, and easily to control. Lately they've have SCR control now that allow you a real fine-tooth control of this kind of technology. So it's works real well at raising the comfort level. But there is a downside. So first, a little schematic of how it works. Again, we're mixing outside air and return air, so we've got a mixture of air and water vapor here. We're condensing a lot of it out, but we come off this coil in the low 50s again, and our space is simply not producing enough heat to keep the balance, right? So it's overcooling, so we have to turn on some kind of reheat. And this can be done with electric, like we saw on the last slide. It can also be done with hot water if we have a source for hot water, and some people do have some waste stream for hot water. That would be ideal. We're looking at actually using solar thermal for this supply of this hot water needs at the UCF. We've got a couple of large solar thermal installations now, and so we're looking at maybe retrofitting some buildings that have boiler systems that are making that hot water with a solar thermal solution. So that would be a very cost-effective way to do it. And then, so the idea here is to get that air conditioned so that raised up a little bit so that it doesn't overcool the space. And so there's a lot of ways to get there. Another thing you could do instead of maybe reheat, a more efficient way and I've seen this retrofitted on buildings. This isn't just for new construction, but this is an enthalpy recovery wheel. This is an actual mechanical device that sits between two different air streams that transfers heat. So diagrammatically here, what happens is the outside air is drawn in, this ventilation that's hot, humid. It might be in the high 80s or low 90s. It comes in and a lot of the heat gets transferred to this wheel. And so on the other side of this wheel, it might have dropped 10 degrees or something. And this wheel rotates, and as it rotates, it moves the heat down to this stream. And this cold air coming out from the building, our building's being conditioned at 73, it comes out, passes across this membrane, and warms that membrane back up. And so that's how that works. Whatever, it transfers the heat from the air coming in to the air going out. So with that system, maybe this heat strip could be completely eliminated, depending on how you set it up. If you get the right mix of temperatures and everything, that could possibly be completely eliminated. And and be big savings for you. So where can this be retrofitted? Anytime you have those two streams near each other, whatever, the closer they are, the more economical it would be to retrofit in your existing building. And we have done that at UCF on a couple of sites where we've been able to make that work as a retrofit project. Another one that we're starting to use that's been around a long time but hasn't gained a lot of popularity is the heat pipe. And this works kind of similar. Here's our cooling coil that we've been seeing in all the pictures. But here we've added two more coils, one on either side of the cooling coil. And the idea here is the same thing, to transfer heat. So this plate warms up a little bit. It moves a closed loop of refrigerant over to this side, and without a pump at all, just due to the forces of heat transfer, it moves that freon around that loop. And so it transfers the heat from one side to the other side. So here we've got some temperatures. We're bringing in air at 80 degrees. These are real temperatures out from a real example. And that's cooled down to a 68 degrees before it hits the coil. So we're using a lot less refrigeration capacity because we're only going from 68 to 53 instead of 80 to 53 like we were before. And then we're reheating that air in a dry way. We're not adding any moisture to it. So we're doing purely sensible, and just like an electric heat strip would do, to get it back up to 65 to go into the space, and that works out. That's actually a really good supply air temperature for a lot of spaces, you know, that would not require any additional heating. So that's a very efficient thing that could be done, and this is actually easier to retrofit than the last one. So I'd encourage you to look at this. There's a bunch of manufacturers out there that make this technology. Talk about controls a little bit. I found this crazy picture on the internet, but I'm a big proponent of controls, but at the same time I want to caution you. So I talk to a lot of people at the university, and I talk to a lot of administrators, and when we're talking about new buildings or whatever, everyone always, you know, the engineers bring in the latest and greatest in controls. And like I said, I'm a big fan. That's where I came from before I came to the university. I was in the control industry. And, but what I always caution people is, don't assume this is true at all. The more controls you put in a building does not automatically return an efficient building at all. In fact, for us, it's been the other direction in some cases, whatever, with brand new construction. So be very careful, and the way you avoid that scenario from going bad with a control situation is, I really encourage the commissioning process. It really got to be in there. These controls have advanced to such a point that the contractor doesn't understand it a lot of times, the engineer doesn't understand it a lot of times, and they're even doing some artificial intelligence now in these controls, and it's really become a big deal. I mean, you can see how much stuff is on this graphic. It's unbelievable. This return plenum right here has 4 different sensors on it coming into this control system. I mean, they're monitoring CO2, they're monitoring humidity, their temperature. They've got modulating valves on the heat, the cool. They've got a modulating VFD speed. They've got everything going on in this thing. And this is an example of this, kind of like what some of our buildings are like, our newer buildings. And I've got a couple case studies at the end here that we can talk about, but about some control issues that have gone wrong in the past. Some strategies that we use that I think are real applicable if you do have a control system on your in your buildings is scheduling. I talked a lot about that, you know, and I can't really. There's not a more powerful technique than, as far as energy reduction, than scheduling is. So I encourage you to try to keep a tight schedule on your buildings. Try to keep it as tight as you can without impacting productivity. Obviously, we don't want to do that. Optimal start and stop, that kind of goes along with scheduling. It's a means to, if you do a setback or a shutdown at night, it's a means to get your building back conditioned perfectly for the people. When the first person walks in the door, you want it to be in perfect condition without using any more energy than you had to. So it tries to predict the perfect time to start up the systems. And it depends on inputs like the outside air temperature and the humidity outside and the indoor conditions and things like that, and how fast your equipment can recover. So it's kind of a complicated one, and that's one of the examples that they use for the artificial intelligence. I was talking about the neural networks that they're using in controls now. They use in that technique. Night setback is a similar thing. That's where we were able to get some gains. And I'm not a big fan of shutting down buildings in Central Florida. I'm more of a fan of the setback. I like to raise the set point when we have an unoccupied building and let it naturally warm up by itself. And what that does is that lowers the relative humidity in the space. And then the next morning we go through this optimal start procedure or whatever and the systems, and I do it in a slow method where we can draw down that moisture. You move that air real slow across the coil, and we're able to really dehumidify the space. So I'd encourage you to look at things like that. Load-based control is kind of looking at your site instead of assuming you've got a certain load going on in there. Look at your terminal units to see what's going on, and it goes along with resetting of the other parameters that are going into the cooling process. Demand ventilation we talked about. Chilled water reset, that's again the same. It's trying to take advantage of savings when there is an opportunity without degrading your building. Condenser water reset, we're going to talk about later. Free cooling we don't use at UCF, although I think there is a small opportunity for it at certain times of year. That's when you bring in unconditioned air into the space and you do cooling. There's just a very limited window in Central Florida for that. Space temperature reset it goes along with the night setback that we do, and then pressure and evening purge. Evening purge is to ramp up the ventilation to clean out the building during the day. We don't use that. We think that we are doing the ventilation properly during the day. Our commissioning team, I'm real proud of. This is the best thing we've got going in our department, and we're the second university in the country to have their own in-house team. They go through many of the things that we saw on the previous slide. They work with primarily the building automation systems, and first they go through and just calibrate everything. So we talked about the control system just being a computer. I mean, in one level, it's just a computer running a set of instructions. So if someone gives it bad instructions, it just does stuff bad forever, and that's why why I don't make the analogy between energy efficiency and controls. But these guys go in, and these are actually two technicians that are going in and calibrating a pump maybe to see and the sensors associated with it to make sure that the computer is getting the right inputs. The next thing they really focus on is temperature unification. So in these multi-zone systems that we have and you have in many of your facilities, you can very easily have simultaneous heating and cooling taking place in two adjacent spaces that are kind of sharing the air. And so as you can imagine, that's super energy intensive. So I talked earlier about that policy.
Walker, please. Dial the operator. Controller Walker, dial the operator, please.
The energy policy that we put in place to unify temperatures across campus, we use that inside the buildings, and you get all the spaces on the same page so that they're not, to prevent that from happening, that fighting. And the next thing again is scheduling. I've talked about that to death. And then finally we work with the actual code, and we don't come up with these ideas on our own. We get them all out of trade magazines, so I encourage you to look at some of those and get the latest, greatest techniques that people are coming up with. The smart people out there is what I call them. I read the stuff, and then I try to implement it. And we're pretty successful doing it. This is a terminal unit inside of one of our buildings, and I just wanted to talk about the mindset or whatever, how I like to think about these things. I like to start at the very end of the thing and move backwards. So I go into a space, and I mean that we've got a complaint about, and measure the parameters, whatever. If I've got a comfortable space, then we're done. If it's within the energy standards or whatever of the space temperatures, then we're done. If it's not, then I start looking at this guy here, the terminal box, at the very end of the equation, and try to optimize that thing as best we can. We're trying to reduce its airflow to as low as we can while maintaining the ventilation rates. When we back that down, this guy automatically backs down because he's got a feedback with the pressure in the duct. So as say this box starts to close down because we've lowered the CFM or something, then this guy backs down. When that guy backs down, then the cooling load backs down on the cooling coil, and that translates back to the refrigeration side, and it starts backing down that. So instead of starting, a lot of people start with the chillers or with the compressors and things like that. I like to start at the other end of the equation and try to optimize in the reverse order, and that's been real successful for us.